Hello and welcome back to another episode of Math with Stone. Today we're going to be talking about pendulums, and we're going to be talking about it and applying it to the conservation of energy, as well as just understanding how pendulums are going to be swinging back and forth and back and forth in a way that kind of conserves both mechanical energy, assuming there is no friction. So with that in mind, what we're going to do is we're going to draw a triangle here to help ourselves out. So with that right triangle, this length right here is the same as this length right here from the top to all the way to the bottom. So that's an important detail. And typically you would see the angle here. I've also seen it down there. I kind of like it at the bottom more, to be honest. But if we want to find anything involving potential energy, we essentially need to figure out what is the change in height. Well, it started up here, and now it ends up down there, so to speak. So we need to figure out this change in height, and that would allow us to figure out how the potential energy has changed. So if the potential energy has changed, then we need to figure out that delta H to figure out the potential energy change, because potential energy is mgh. So that's the harder part. Across from this angle, we got our opposite. Here, that would leave our adjacent, which means that this guy over here, this side from here to here, that would be equal to cosine of theta would equal adjacent over L. And if we solve for the adjacent side, we would end up figuring out that this side over here is L times cosine of theta. That would equal our adjacent side. All right, with that in mind, there's still more, but wait, there's still more. There's a lot to this one, a lot. With that in mind, remember, we're looking for delta H. We don't really care. Well, we needed this part, but we don't really care about this part. If this part right here is L times cosine of theta, and remember how I said in the very beginning, this whole string goes all the way down, and the whole thing, oh, that was the worst. That whole thing is L from top to bottom. What would be delta H? Well, if you take the whole thing L and subtract this L cosine theta, you would get delta H. So that tells us that our change in height is equal to the full length minus L cosine of theta. And it's not necessary, but it is very helpful to factor out an L here to give us 1 minus cosine of theta. A lot of times you will see the L represented as an R for the radius, because it's kind of like a circle when you think of it swinging around here. All right, that just told us our delta H. Calculate the potential energy of this, this at, probably let's go with the dot right here, but it really doesn't matter. So the potential energy, the change in potential energy, we would need to do mgh, and we just found out our change in height. So our mass, we don't know. So our change in potential energy, which we could call UP or just U, would equal our mass times gravity times all of this stuff, which would be L times 1 minus cosine of theta. All right, so that's part one. Part two, calculate the speed of the bob at the bottom of the swing. Okay, so with that in mind, you also have to consider and think really hard about how and what is even occurring. All right, so here we are going to take into consideration our conservation of energy formulas. The change in kinetic energy, your kinetic energy initially, and then our potential energy initially must equal our kinetic energy final plus our potential energy final. Okay, so with that in mind, we know that the change in potential energy was this stuff. So we're going to plug that in. We also can know our kinetic energy initial and some other stuff. So let's think about initially, if we were up here, what is the speed at this ball? Well, it's starting to like change from going up to down. So the speed initially would be 0. So that means that the 1/2 mv squared would just kind of cancel out. We also know that the overall change in potential energy, if we subtracted the UF here, we would get our change in potential energy, delta U, must therefore equal the change in, not change in kinetic energy, but essentially the final kinetic energy. And we want to know the speed at the bottom, which would be its final in this case, because that's where we're stopping. So delta U, we figured out, was mg times L. Oh, I forgot the L here. I'm sad. mgL times... No, I didn't forget the L. I messed up my parentheses. mgL times 1 minus cosine theta. My formula looks ridiculous. I should have just put this right here, right in front of the M and the G. So I'm going to rewrite that. mgL 1 minus cosine theta. There we go. That looks better. I keep forgetting the L when I was doing this problem earlier. mgL times 1 minus cosine theta. That is the change in potential. That would have to equal the kinetic energy final. Well, the kinetic energy of anything is 1/2 mv squared. So if we solved for the f squared part, the vf squared part, we would have to multiply by 2 and divide by m. If we multiply by 2 and divide by m, dividing by m, the m's would cancel out, giving us 2gl times 1 minus cosine theta would equal a vf squared. And if we solve for that velocity, we would square root, and we would figure out the final velocity is equal to the square root of 2gl 1 minus cosine theta, and that would be part B. Okay, so that is part B. Another thing that I would highly suggest doing, let me see if I can find it, is recognizing what is occurring with a pendulum in general. Where'd it go? Where'd it go? I had a diagram. Diagram is missing. Everything is wrong in the world. Okay, I'll draw the diagram myself. I'm sad. I gotta draw things myself. Kind of want to keep looking for it, but that's okay. That would be that with a spring, not a spring, with a pendulum, if you think of kinetic energy versus potential energy, the kinetic energy at the top of the spring pendulum would be 0. As it moves from here to here on the pendulum, the kinetic energy is being converting from potential to kinetic, so it's going to go up as you get to the bottom. So this would be when we're at the bottom right here, bottom. That would be when kinetic energy is at its highest. And then as it goes back up to this portion, then it would be converting back into potential energy and would go back to 0. And this process is going to repeat over and over again. Potential energy would do the opposite. Potential energy, when it's at the top, would be at its highest, and then when it gets to the bottom, all that potential energy will have been used up in terms of kinetic energy and converted, and then it would come back up once we got to the top again. So this would be here as well as here, but in general, in terms of timeline, it would be the second one. All right, I've rambled enough. Continue on with your studies, my friends. I will see y'all in the next one. Bye.